Friday, April 13th, 2029. Write that date down, because it's the day humanity gets to watch a cosmic game of roulette play out in real time. An asteroid named Apophis, yes, after the god of chaos, is going to pass so close to Earth that it'll fly between us and our own satellites. Close enough that you won't need a telescope to see it. Just look up. Now, 3I Atlas recently passed through our solar system, and everyone relaxed because it posed zero threat. But Apophis isn't 3I Atlas. This one isn't passing through. It's been circling us for eons. And during those 7 hours in 2029, Earth's gravity is going to reach out and either push it away forever or pull it onto a trajectory that brings it back, with considerably more violent intentions. Stay until the end, because the math that determines which outcome we get is so precise, so razor thin, it'll make you question everything you thought you knew about safety in space. Don't go anywhere, because the story of Apophis gets stranger the deeper we dig. Hit that subscribe button and stay close, because what happens in those 7 hours of flyby could rewrite everything we thought we understood about asteroid threats. Space keeps its cards close to the chest, but by the end of this, we'll know whether Friday the 13th is just another date on the calendar or the beginning of a countdown we're not ready for. Something strange happened in the winter of 2024. An object from beyond our solar system, cataloged as 3I Atlas, made its way through our cosmic neighborhood and slipped past us without so much as a whisper. The headlines were polite, almost clinical. Scientists observed it, measured it, confirmed it came from interstellar space, and then watched it leave. There were no emergency meetings, no doomsday countdowns, no disaster movies greenlit in its honor. It arrived, it ignored us completely, and it left. The universe, it seemed, was telling us something comforting. We are not interesting enough to destroy. But here's the problem with that comfort. While 3I Atlas was making its harmless exit, while the world was collectively exhaling and returning to concerns about inflation and celebrity scandals, we missed something critical. We interpreted cosmic indifference as cosmic safety. We assumed that because one visitor from the void showed us mercy, the universe itself must be essentially benign. The scientific community made careful, measured statements. AP News reported what every astronomer already knew. 3I Atlas isn't near Earth and poses no risk. The object was millions of kilometers away at its closest approach, barely a blip on our existential radar. It was the perfect non-story, the ideal example of a threat that never was. This is where human psychology betrays us. We saw an interstellar object drift through our solar system like a tourist in a museum, looking but not touching, and we extrapolated safety from that encounter. If the truly exotic objects, the ones that come from light years away, the ones that have traveled through the frozen darkness between stars, if those objects ignore us, then surely the familiar rocks in our own solar system must be even less dangerous, right? The logic seems sound until you realize it's completely backwards. Think about it this way. A stranger who walks past your house without looking at you is, statistically, unlikely to break in. But a stranger who keeps circling your block, studying your windows, noting when you leave for work, that stranger has moved from indifference to interest. And interest, in the language of orbital mechanics, is spelled Gravity. Enter 99942 Apophis, named after the ancient Egyptian god of chaos and darkness. Where 3I Atlas was the cosmic equivalent of a ship passing in the night, Apophis is something entirely different. This is not an interstellar wanderer. This is a neighbor, a very close neighbor. And unlike the polite visitor from beyond, Apophis has been circling our planetary block for millions of years, its orbit intersecting with Earth's in a gravitational dance that scientists first noticed in 2004. When astronomers at the Kitt Peak National Observatory first spotted Apophis on June 19, 2004, They had no idea what they'd found. It was just another near-Earth asteroid, another dot of light moving against the background stars. But as they calculated its trajectory, as they worked out where it had been and where it was going, something alarming emerged from the mathematics. This rock, this 340-meter wide chunk of stone and metal, was on a collision course with statistical significance. Within days of its discovery, Apophis had achieved something no asteroid had done before. It reached level 4 on the Torino impact hazard scale. To understand how extraordinary that is, you need to know that the scale goes from 0 to 10, and nothing in modern history had ever climbed above level 2. Level 4 means roughly a 1% chance of a collision capable of regional devastation. That might not sound terrifying until you realize that 1% is astronomical when it comes to cosmic impacts. These are odds that make insurance companies nervous. These are odds that make governments create task forces. For a brief electric moment in December 2004, Apophis held a 1 in 37 chance of hitting Earth on April 13th, 2029. 1 in 37. You have worse odds at a roulette table, better odds of picking a face card from a shuffled deck. The contrast couldn't be more stark. 3I Atlas, distant, fleeting, fundamentally unconcerned with Earth's existence. Apophis, close, returning, gravitationally entangled with our planet's future. One object came from the void and returned to it, a cosmic messenger that delivered no message. The other object has been here all along, caught in the sun's gravity well, just as we are, its orbit crossing ours like two dancers who keep almost colliding on a crowded floor. This matters more than you might think. The cognitive shift from space is empty and safe to space is crowded and dangerous represents a fundamental rewiring of how we understand our place in the solar system. For most of human history, the sky was static, predictable, essentially harmless, except for the occasional meteorite. The discovery of asteroid impacts as extinction events changed that, but even then, the threats seemed theoretical, distant in time, unlikely in our lifetimes. 3I Atlas reinforced our sense of cosmic isolation. We could watch an interstellar visitor come and go, and nothing changed. No drama, no danger, just another data point for astronomy papers. But Apophis forces us to confront a different reality. The universe isn't dangerous because it hates us or targets us. The universe is dangerous because of familiarity, because of proximity, because gravity doesn't care about our hopes and fears. It just calculates. It just pulls. And when objects share orbital space for long enough, eventually, probability catches up with possibility. So here's the thesis that will haunt the next 8 years of your life. Indifference from the universe feels safe because it leaves us alone. Familiarity, repeated visits, gravitational interactions. These feel dangerous because they create opportunities for catastrophe. 3I Atlas was never going to hit us precisely because it was passing through. Apophis might hit us precisely because it keeps coming back. The countdown has already begun, and unlike that distant interstellar wanderer, this time, the universe is paying attention. Friday, April 13th, 2029. Mark that date. Memorize it. Because on that day, something is going to happen that hasn't occurred in recorded human history. An asteroid the size of a cruise ship is going to pass between Earth and our own satellites, skimming just 31,000 kilometers above our heads. To put that in perspective, the International Space Station orbits at roughly 400 kilometers. The Moon sits at 384,000 kilometers. Apophis will thread the needle between our planet and our technology, close enough that you could, theoretically, shine a powerful laser at it and get a reflection back in a fifth of a second. NASA's tracking data confirms what sounds like science fiction. This is not a distant observation. This is an encounter. 31,000 kilometers sounds like a lot until you realize that geostationary satellites, the ones that provide your weather forecasts and satellite television, orbit at approximately 35,000 kilometers. Apophis is going to pass inside that ring. It will fly through a region of space so crowded with human technology that engineers are already calculating whether any satellites might need to be moved. The object isn't coming close to Earth. It's coming close to civilization. But here's where it gets psychologically strange. Apophis will be visible to the naked eye. Not through a telescope, not through binoculars, just standing in your backyard, looking up. It will appear as a bright point of light moving across the sky, tracking from the Indian Ocean across Africa and the Atlantic, visible to roughly 2 billion people across Europe, Africa, and Western Asia. Imagine that for a moment. 2 billion people simultaneously watching a mountain-sized rock slide pass their planet in real time, fast enough to cross the width of the moon in less than an hour. Now, naked eye visibility might seem like a fun astronomical event, a cosmic spectacle to share on social media, but it's actually a symptom of something much more significant. When we can see an asteroid without optical aid, it means the object has entered a regime of proximity so unusual, so statistically rare, that our intuitions completely fail us. The human eye can see objects in space under very specific conditions. They must be large enough, reflective enough, and close enough to gather sufficient light. Apophis checks all 3 boxes, but it's that third factor, closeness, that transforms this from an observation into a dynamical event. Because Earth isn't just attracting Apophis in some passive, gentle way. Gravity doesn't work like that. When an object passes this close to a planet, gravity doesn't simply pull it closer and let it go. Gravity interrogates it. Gravity reaches into the object's trajectory and twists it, torques it, fundamentally alters its future path through space. The United Nations Office for Outer Space Affairs has noted that passing inside geostationary orbit is astronomically rare for an object this size. We're not talking about a close call that happens every few decades. We're talking about an event that, statistically, should occur once every several thousand years. What happens during that pass is where orbital mechanics becomes almost violently counterintuitive. Apophis is traveling at about 7.4 kilometers per second relative to Earth during the encounter. That's fast enough to cross the continental United States in about 6 minutes. But from Earth's perspective, watching with billions of years of gravitational authority, that speed is manipulable. Our planet's gravity field will grab Apophis and deflect it, changing its velocity vector, altering its orbital period, essentially rewriting where it will be at every moment of its future existence. Think of it like this. Imagine a car approaching an intersection at high speed. Now, imagine the intersection itself can reach out and change the car's direction without physically touching it. That's what Earth does to Apophis on April 13th, 2029. We bend its path, we change its future, and in doing so, we create the possibility that 7 years later, on April 13th, 2036, that future could include another intersection, another close pass, one that might not be quite as generous. The science that describes this process has a term: gravity perturbations. Every massive object in space creates a dimple in space-time, and when other objects pass through that dimple, their trajectories change in ways that depend on speed, distance, angle of approach, and about a dozen other variables that require calculus to properly describe. For Apophis, the 2029 flyby represents a massive perturbation event. Earth's gravity will pull on different parts of the asteroid with different strengths, creating tidal forces, stressing its structure, potentially changing its rotation rate, and definitely, absolutely, without question, changing where it goes next. Scientists have run the calculations thousands of times. They've mapped the trajectory with radar observations, optical tracking, and computer models that simulate millions of possible futures. The current assessment, released by NASA and verified by independent researchers worldwide, is that the 2029 pass will deflect Apophis into a slightly different orbit, but one that definitively does not intersect with Earth in 2036. The odds of an impact have been reduced to essentially zero, at least for that particular date. But here's the thing that keeps some scientists awake at night, the detail that doesn't make it into the reassuring press releases. Precision in orbital mechanics is never absolute. We know where Apophis will be on April 13th, 2029 to within a few kilometers. That's extraordinary precision, the result of decades of observation and increasingly sophisticated tracking technology. But that precision degrades over time. The farther into the future we try to predict, the larger our uncertainty becomes. And that uncertainty is driven by forces so small, so subtle, that they barely register in our equations. Thermal effects, for example. As Apophis rotates, one side heats up in the sun while the other cools in shadow. That temperature difference creates a tiny jet effect, an infinitesimal thrust that, over years and decades, can shift the asteroid's position by kilometers. We call it the Yarkovsky effect, and it's measurable, predictable to a degree, but never perfectly. Solar radiation pressure, gravitational influences from other asteroids, even the outgassing of volatiles if Apophis contains any water ice. All of these contribute to an error budget that compounds over time. So when scientists say Apophis is safe for 2036, they're speaking with tremendous confidence based on current data. But they're also acknowledging, in careful technical language, that orbital mechanics is a game of probability, not certainty. The asteroid isn't passing through our neighborhood like 3i Atlas, indifferent and untouchable. Apophis is checking in, gravitationally engaged, part of a system that includes Earth as a major player. And in systems like that, tiny changes can have enormous consequences, which raises an uncomfortable question. If gravity is the great decider, if these close encounters write the future in invisible ink, what else might change during those 7 hours when Apophis crosses through our orbital space? What can't we measure? What don't we know? Imagine space as an ocean and Earth as a massive whirlpool. Any object that gets too close doesn't just get pulled, it gets steered. Its future trajectory determined by exactly how it enters the whirlpool's influence. Now imagine that within this whirlpool, there are specific channels, narrow corridors of space, where an object entering in exactly the right way, at exactly the right angle, at exactly the right speed, gets flung not just away from Earth, but onto a return path that brings it back for another encounter. These channels are real. They're measurable, and in the terrifying vocabulary of planetary defense, they're called gravitational keyholes. The term sounds almost poetic until you understand what it actually means. A gravitational keyhole is a region of space, sometimes only a few hundred meters across, that acts as a gateway between safe passage and catastrophic return. If an asteroid passes through one of these keyholes during a close approach, Earth's gravity will alter its orbit in such a precise way that it returns years later on a collision course. It's not magic, it's just Newton's laws playing out across scales we can barely visualize. The asteroid doesn't know it's passing through a keyhole. Space itself doesn't change. But the mathematics of orbital mechanics creates these invisible boundaries where futures diverge. When Apophis was first discovered in 2004, scientists quickly realized they had a problem. The observation arc, the amount of time they'd been tracking the asteroid, was incredibly short. Just a few nights of data, a handful of position measurements against the background stars. From that limited information, they had to calculate where Apophis had been for the last several million years, and where it would go for the next several decades. The mathematics is well established, but the uncertainty in those early calculations was enormous. Apophis could be almost anywhere within a broad swath of possible orbits, and some of those possible orbits passed through a keyhole, specifically a keyhole that would set up an impact in 2029. That's what triggered the Level 4 Torino rating, the 1 in 37 odds that briefly made Apophis the most dangerous object in near-Earth space. The keyhole itself was calculated to be roughly 600 meters across, a tiny target in cosmic terms, but large enough that the asteroid's position uncertainty at the time included it as a real possibility. Then, something remarkable happened. Astronomers kept watching. They tracked Apophis night after night, expanding the observation arc, shrinking the uncertainty. With each new data point, the possible orbits narrowed. And as they narrowed, scientists could calculate with increasing precision exactly where Apophis would be during its 2029 flyby. By 2006, enough data had accumulated to rule out the 2029 keyhole entirely. NASA downgraded the hazard rating. The immediate threat evaporated, replaced by relief, and, in some quarters, a sense that we'd dodged a bullet we never fully understood. But here's what doesn't get emphasized enough in the public messaging. Keyholes don't disappear. They're not temporary features that vanish when we stop worrying about them. They're permanent mathematical structures embedded in the three-body problem of Sun, Earth, and asteroid. What changed wasn't the existence of the keyhole. It was our understanding of where Apophis would be relative to it. We didn't remove the danger. We refined our knowledge of the danger's location. And that refinement is only as good as our ability to measure and predict forces that operate on scales smaller than our instruments can reliably detect. This is where the conversation gets uncomfortable for people who want simple answers. Most scientists, asked directly about Apophis, will tell you it's safe. The data supports that conclusion. The observations are extensive, the models are robust, and the trajectory is well constrained. But ask those same scientists whether they're still monitoring for keyholes, whether they're still running scenarios that include gravitational deflection into return orbits. And the answer is always yes. Not because they expect disaster, but because uncertainty, however small, never completely vanishes. The Yarkovsky effect alone introduces position errors that grow over time. For Apophis, the uncertainty in its position decades from now includes a margin of several kilometers. That sounds tiny until you remember that some keyholes are only hundreds of meters across. We're playing a game where the target keeps moving, the projectile has a margin of error, and the stakes are measured in megatons of kinetic energy. And there's another layer to this that rarely gets discussed outside technical conferences. Gravitational keyholes aren't just sensitive to position, they're sensitive to velocity. An asteroid moving just a few centimeters per second faster or slower can miss or hit a keyhole, depending on the geometry. And velocity, like position, is subject to perturbations we can model, but not perfectly predict. Solar wind pressure, gravitational tugs from Mars or Venus during distant encounters, even the redistribution of mass within the asteroid itself, if it's a rubble pile held together by weak self-gravity. All of these can alter velocity by amounts that seem negligible until you run the equations forward through multiple close approaches. So when scientists say Apophis won't hit Earth in 2036, they're making a statement based on probabilities that are extraordinarily favorable, but not metaphysically certain. They're saying the current trajectory, with all known perturbations accounted for, does not include a path through any dangerous keyhole during the 2029 encounter. But they're also running continuous updates, checking for unexpected changes, monitoring the asteroid with radar every time it comes within detection range. Because in orbital mechanics, confidence is built on data, and data requires vigilance. There's a philosophical question buried in all this technical detail. At what point does a small enough probability count as impossible? 1 in a million? 1 in 10 million? The asteroid that killed the dinosaurs had zero probability of impact until the moment it entered Earth's atmosphere. Probability is a statement about our knowledge, not about reality. Reality just does what the equations say it will do. And the equations for Apophis include terms, however small, that represent pathways through gravitational space we'd rather not think about. But we do think about them. Scientists think about them constantly, because the 2029 flyby isn't just a spectacle. It's a test of our models, our instruments, our ability to predict the behavior of objects moving at kilometers per second through gravitational fields we're still learning to fully characterize. If tiny unmeasured forces exist, if there are effects we haven't accounted for, April 13th, 2029 will reveal them. And what we learn in those hours could rewrite every calculation we've made about what happens next. Which brings us to something even stranger than keyholes. Something that doesn't show up in most orbital predictions, because we've never seen it happen in real time. What if the asteroid itself changes? Apophis is not a solid rock. This is the first thing you need to understand if you want to grasp what might happen on April 13th, 2029. We don't have a sample. We haven't landed a probe on it, but radar observations and spectroscopic analysis give us a fairly clear picture. Apophis is what planetary scientists call a rubble pile. It's a loose collection of boulders, gravel, and dust, held together by its own weak gravity, and possibly some cohesive forces we don't fully understand. Imagine a beanbag the size of a skyscraper, tumbling through space at 17,000 miles per hour. That's Apophis. Now imagine what happens when that beanbag passes within 31,000 kilometers of a planet with a gravity field strong enough to hold the moon in orbit. Earth doesn't just pull on Apophis as a whole, it pulls on every individual piece of rock inside it, and it pulls harder on the side, closer to Earth than the side farther away. This differential force is called tidal stress, and it's the same phenomenon that creates ocean tides on Earth that ripped Comet Shoemaker-Levy 9 apart before it slammed into Jupiter in 1994. Tidal stress during the 2029 flyby won't be strong enough to completely shatter Apophis. The calculations are clear on that point, but they might be strong enough to do something almost as significant. They might change how the asteroid spins. Rotation is not a trivial detail in asteroid dynamics. The way an object spins affects how it absorbs and radiates solar energy, which directly influences the Yarkovsky effect we talked about earlier. More importantly, if Apophis is a rubble pile, its rotation state is essentially an equilibrium between gravitational self-attraction and centrifugal force trying to fling pieces apart. Change the rotation rate or axis, and you change that equilibrium. You potentially trigger internal readjustments, shifts in the distribution of mass, even surface landslides as loose material responds to new forces. A study published in 2023, examining the effects of close planetary encounters on rubble pile asteroids, suggested that tidal stress during flybys can induce seismic shaking strong enough to cause surface regolith to flow like a liquid. The term they used was tidal excitation of seismicity. In plain language, earthquakes, or more precisely, asteroid quakes. The research indicated that objects passing as close as Apophis will, in 2029, could experience tremors that reshape their surface, alter their internal structure, and change their mechanical properties in ways that don't immediately affect the overall orbit, but could have delayed consequences. Think about what that means. Apophis approaches Earth as one configuration of rock and dust. It passes through our gravity field, experiencing forces it hasn't felt in millions of years, possibly ever. Those forces shake it, spin it, stress it, and then it leaves, continuing on its new trajectory, but potentially with a different rotation rate, a different surface topography, maybe even a different density distribution if internal voids collapse or expand. We won't know immediately. Radar can tell us the overall shape, But detecting subtle internal changes requires observations we're only beginning to have the technology to perform. And here's where this gets genuinely concerning. If Apophis changes during the flyby, if its spin state or internal structure shifts in ways we don't detect right away, those changes will affect how it responds to solar radiation. They'll modify the Yarkovsky drift. They'll introduce new uncertainties into our trajectory predictions for subsequent orbits. We might think we know where Apophis will be in 2036, 2043, 2050, but those predictions are based on an asteroid that hasn't yet experienced the most significant gravitational encounter of its existence. Live Science reported on research suggesting that close flybys could trigger surface landslides visible from Earth with high-resolution imaging. Imagine watching in real time as an asteroid reshapes itself, boulders tumbling down slopes that didn't exist an hour before, dust clouds expanding in the vacuum of space. It would be spectacular science. It would also be terrifying, because every change to the asteroid's physical state is a change to variables in equations that determine its future path. There's a historical precedent here, though not a perfect one. When comet Shoemaker-Levy 9 approached Jupiter in 1992, tidal forces didn't just alter its orbit, they completely destroyed it. The comet broke into more than 20 separate fragments, each following slightly different trajectories, all of which eventually collided with Jupiter over the course of a week in July 1994. Now, Apophis is far more structurally robust than a comet, and Earth's tidal force at 31,000 kilometers is much weaker than Jupiter's at its Roche limit. But the principle is the same. Close approaches don't just change where an object goes, they can change what an object is. NASA's Planetary Defense Office is aware of these possibilities. They've stated publicly that the 2029 flyby represents an unprecedented opportunity to study an asteroid during a close Earth encounter. They plan to have multiple instruments trained on Apophis as it passes. Radar systems to map its shape in 3 dimensions, spectrometers to analyze its composition, optical telescopes to track any changes in brightness that might indicate rotation rate changes. This isn't just curiosity. This is data collection for a threat assessment that extends decades into the future. But there's a gap between what we can observe and what actually matters. We can measure Apophis's surface to a resolution of a few meters with radar. We can determine its overall rotation period to within seconds, but we can't see inside it. We can't map the internal structure, the distribution of voids and solid rock, the way forces propagate through the rubble pile during tidal stress events. Those internal details determine how the asteroid responds to perturbations, and they're essentially invisible to remote observation. So here's the thought that should keep planetary defense experts awake. What if Apophis exits the 2029 encounter subtly changed in ways we don't immediately detect? What if its rotation axis shifts by a few degrees? Or its internal friction coefficient increases because loose material settles into new configurations? Or volatile ices we didn't know existed sublimate from the heat of tidal flexing? Any of those changes would alter the asteroid's future trajectory in ways our current models don't predict, because our current models are built on an asteroid that hasn't experienced this encounter yet. We're not talking about science fiction scenarios. We're talking about known physics applied to an object we've never fully characterized. And the gap between those two things, between what we know and what we need to know, is where uncertainty lives. Uncertainty in orbital mechanics doesn't mean ignorance. It means acknowledging that reality is more complex than our models, and sometimes reality surprises us. The question isn't whether Apophis will change during the 2029 flyby. It almost certainly will, at least in subtle ways. The question is whether those changes will matter. And we won't know the answer to that until well after the asteroid has already left, carrying its secrets into an orbit we're still trying to predict. There's a fascinating tension in how institutions talk about Apophis. And if you pay attention to the language carefully, you start to notice a pattern. To the public, the message is clear and consistent. Apophis poses no threat. NASA's website states it unambiguously. The European Space Agency concurs. Every major scientific body that tracks near-Earth objects agrees that based on current data, the probability of impact in the foreseeable future is effectively zero. The press releases are calibrated for reassurance, the interviews with astronomers are measured and calm, the overall narrative is one of a danger identified, studied, and ultimately dismissed. But then you look at what those same institutions do behind the scenes, and a different picture emerges. Apophis is the centerpiece of planetary defense exercises. It's the asteroid that NASA uses when training emergency response teams. It's the scenario that gets run through computer simulations at international conferences on impact mitigation. When the United Nations Office for Outer Space Affairs convenes meetings about asteroid threats, Apophis is the example they return to again and again. Not because it's dangerous in the immediate sense, but because it's pedagogically perfect. A real object on a known trajectory, close enough to study in detail, and historically significant enough that everyone in the field knows its parameters. This is not deception, exactly. It's more like the difference between a fire drill and a fire. You practice evacuating the building even when there's no smoke, precisely so you'll know what to do if real flames appear. Apophis serves that function for planetary defense. It's the drill, the controlled scenario, the asteroid we point to when we want to demonstrate our capabilities and identify our limitations. But here's where it gets psychologically complex. The public hears no threat, while institutions treat Apophis as the gold standard worst-case training scenario. That gap creates a cognitive dissonance that's hard to reconcile. If it's safe, why the obsessive attention? If it's dangerous, why the reassuring language? The answer is that both things are true simultaneously, depending on your time horizon and your tolerance for uncertainty. On timescales of the next few decades, based on everything we know, Apophis is safe. It won't hit Earth in 2029. It won't hit in 2036. The math is solid. But on timescales of centuries, with multiple close approaches compounding uncertainty, with gravitational keyholes lurking in the probability distributions like landmines in a fog, the same object becomes a model for how small risks accumulate into larger ones. It's the asteroid that makes scientists think about what could go wrong, not what will go wrong. NASA has stated explicitly that they're treating the 2029 flyby as a natural experiment. They'll gather more data about Apophis during those few hours than they've collected in the entire 20 years since its discovery. That data will refine models not just for Apophis, but for every similar asteroid in near-Earth space. The flyby is a chance to test our tracking systems, our prediction algorithms, our understanding of how objects respond to gravitational perturbations. It's science in real time, high-stakes research with an asteroid that helpfully refuses to actually threaten anyone while still coming close enough to matter. But there's a cynical reading of the situation that's worth considering. Institutions speak in different registers to different audiences. To the public, you emphasize safety because panic serves no purpose and would undermine trust in scientific expertise. To internal teams, you emphasize preparedness because complacency is more dangerous than anxiety. The question is, where do those two narratives diverge? And more importantly, if future observations revealed a non-zero probability of impact, would institutions disclose it early, when uncertainty is still high and the public might not understand the nuances? Or would they manage the information more carefully, releasing details only when confidence levels reach thresholds that wouldn't trigger mass hysteria? We have precedent for this kind of information management, though not with asteroids. When 3I Atlas was first detected, there was a brief period where its trajectory wasn't well constrained. Some early projections suggested it might pass closer to Earth than initial estimates indicated. That information was shared in scientific channels immediately, but it took time to filter through to public awareness, partly because the uncertainty resolved quickly. But imagine if it hadn't. Imagine if the uncertainty had persisted for weeks or months while scientists tried to pin down whether an interstellar object might actually pose a risk. How would institutions have handled that? What would they have said, and when would they have said it? Apophis gives us a template. When the Level 4 Torino rating was announced in 2004, NASA didn't hide it. The information was public, accessible, reported in mainstream media. But the framing was always careful. Emphasis on uncertainty, on the need for more observations, on the expectation that refined data would reduce the risk. And that's exactly what happened. The rating dropped to level 1 within weeks, then to 0 within months. The narrative arc went from possible threat to false alarm to interesting science in less than a year. But what if it hadn't? What if each new observation had narrowed the uncertainty in the wrong direction, toward a keyhole instead of away from it? At what point does "we're monitoring the situation" become "you should prepare for potential impact"? And who makes that call? The planetary defense community has protocols for this. The International Asteroid Warning Network has communication strategies, escalation procedures, frameworks for coordinating information release across countries and agencies. But protocols on paper and protocols under pressure are different things. The first time we actually need to tell the global population that an asteroid is definitely going to hit Earth somewhere, sometime, those protocols will be tested in ways no simulation can fully anticipate. And here's the uncomfortable truth. We might not get much warning. Not because we're not looking, but because the objects most likely to hit us are the ones we find late. The detection paradox is real. Our telescopes are getting better. Our AI algorithms are improving. We're discovering more asteroids than ever before. But we're discovering them when they're already relatively close, because that's when they're bright enough to detect. 3I Atlas wasn't found until it was already well into the solar system. If it had been on a collision course, we'd have had maybe a year to respond. Maybe. Apophis is different, because we found it early, because its orbit brings it back repeatedly, because we've had 2 decades to study it. But most asteroids aren't Apophis. Most of them are dark, small enough to escape detection until they're almost here, moving too fast for interception if we wanted to try. Planetary defense is built on the assumption that we'll see the threat coming, that we'll have years or decades to mount a response. But that assumption only holds for objects we've already cataloged, objects whose orbits we already know. The real countdown isn't to impact. It's to understanding. Understanding what's out there, what's coming, what we can actually do if the math stops being reassuring. And that understanding is incomplete. It will always be incomplete. The universe is too big, space is too dark, and the number of objects that could end civilization is larger than the number we found. So when NASA says Apophis is safe, believe them. The data supports that conclusion. But when they keep running planetary defense exercises using Apophis as the scenario, pay attention to that too. Because the exercise isn't about Apophis specifically. It's about everything Apophis represents. The asteroids we know about but can't perfectly predict. The asteroids we don't know about at all. And the gap between our capabilities and what the universe might ask of us. The theater isn't the reassurance. The theater is pretending we have more control than we actually do. And sometimes, just sometimes, the universe calls that bluff. December 2024 is a strange time to be watching the sky. While most of the world is preoccupied with holiday preparations and year-end summaries, astronomers are tracking something that should make everyone pause and think about what else might be out there, silently approaching. 3I Atlas is making its closest approach to the Sun right now, swinging through the inner solar system on a trajectory that will carry it back into the void from which it came. Space.com and other science outlets are reporting fresh observations, new data about its composition and velocity, refinements to our understanding of interstellar objects in general. But here's what's remarkable about that reporting. We're getting new data about 3I Atlas now, in late 2024, even though the object was first detected months ago. This isn't because scientists were slow to analyze it. It's because the object is only now becoming bright enough, only now passing close enough to the sun, to reveal certain spectroscopic details that weren't accessible earlier. We're learning about this visitor on its way out, not on its way in. And that pattern, that delayed revelation of information about objects already in our cosmic neighborhood, is becoming disturbingly common. The paradox of modern asteroid detection is this. We have better telescopes than ever before, more sophisticated search algorithms, AI systems that can scan thousands of images per night, looking for anything that moves against the background stars. We're finding more objects than at any point in human history. And yet, we're finding many of them late, not because our technology is failing, but because there's a fundamental limit to how early we can detect something. An asteroid or comet is only visible when it reflects enough sunlight back toward Earth for our instruments to register it. Small objects, dark objects, objects on trajectories that keep them far from the sun until the last moment, these remain invisible until they're already uncomfortably close. 3I Atlas is a perfect example. It's a few kilometers across, large by most standards, and we still didn't detect it until it was already well into the solar system. If it had been aimed at Earth instead of just passing through, we'd have had perhaps a year to notice, panic, and fail to do anything meaningful about it. A year sounds like enough time until you realize that designing, building, launching, and executing an asteroid deflection mission currently takes at least 5 to 10 years with existing technology. The timeline doesn't work. The physics doesn't care. And this isn't a one-off situation. Astronomers are detecting more interstellar objects now than ever before, but that's partly because more than ever before is a low bar. We've only confirmed a handful of interstellar visitors in all of human history. 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I, Atlas. 3 objects in 7 years. That's an acceleration of discovery, but it's also a reminder that until very recently, we couldn't detect these objects at all. How many passed through unnoticed in the decades before our detection capabilities improved? How many are out there right now, approaching from angles we're not watching as carefully? This connects directly to Apophis in a way that isn't immediately obvious. We think about asteroid threats in 2 categories: known objects on tracked orbits and unknown objects that might someday appear. Apophis is category 1, the comfortable category, the one where we have data and models and predictions. But the broader pattern, the acceleration of late detections, suggests that category 2 is larger and more active than we want to admit. We're swimming in a shooting gallery we're only beginning to map. The technology is improving, which is both encouraging and terrifying. AI-assisted sky surveys can now process more data in a single night than human astronomers could analyze in a month. Machine learning algorithms are getting better at distinguishing asteroids from camera artifacts, at predicting orbits from minimal observation arcs, at prioritizing which objects need immediate follow-up observations. We're building a detection network that's more capable than anything we've had before. But capability isn't the same as coverage. There are blind spots, large sections of sky that don't get monitored continuously, orbits that approach from the direction of the sun, where the glare makes detection nearly impossible until the object has already passed, objects that are compositionally dark, reflecting so little light that they remain invisible, even when relatively close. We're finding more because we're looking better, but we're still not looking everywhere, all the time, at all wavelengths. The gaps in our coverage are gaps where catastrophe could quietly assemble. Consider the numbers. There are roughly 25,000 known near-Earth asteroids as of late 2024. That sounds like a lot until you realize it represents only the objects larger than about 140 meters that we've managed to detect so far. Estimates suggest there might be another 25,000 or more in that size range still undiscovered. And if you include smaller objects, the ones that could still level a city even if they wouldn't cause a global catastrophe, the number climbs into the hundreds of thousands or millions. We've cataloged perhaps 5% of the total population of potentially hazardous objects in near-Earth space. 5%. That's not a comforting margin. That's a rounding error masquerading as comprehensive knowledge. And the pattern with interstellar objects makes it worse. We now know that our solar system is regularly visited by rocks and ice balls from other star systems. The frequency is still being established, but current estimates suggest 1 or 2 interstellar objects of detectable size pass through the inner solar system every year. Most of them we miss. 3i Atlas is one of the lucky cases where we happen to be looking in the right direction at the right time with the right instruments. But for every interstellar visitor we detect, there could be dozens slipping past unnoticed, their trajectories unknown, their compositions mysterious, their potential threat unassessed. This isn't paranoia. This is mathematics. The solar system is enormous. Our detection capabilities cover a tiny fraction of the relevant volume, and objects move faster than our reaction time allows. We live in a cosmic environment that's far more dynamic, far more populated, far more potentially dangerous than the static, empty space we imagined a century ago. Apophis feels different because we found it early enough to watch it for 2 decades, to refine our predictions, to build confidence in our models. But Apophis is the exception, not the rule. Most asteroids don't give us that luxury. Most of them announce themselves only when they're already too close to ignore, and possibly too close to deflect. The question that keeps coming up in planetary defense circles is whether we're entering a denser orbital region, whether the solar system's local environment is more crowded now than it was in the past, or whether we're just finally developing the eyes to see what was always there. The answer is probably the latter, but it's unsettling either way. If the threats were always present and we're only now noticing them, that means we've been lucky. And luck is not a strategy. So while 3i Atlas makes its way back into the interstellar darkness, while we collect data on an object that never threatened us, remember what that detection represents. It represents our improving ability to see what's coming, but also our continuing inability to see everything. It represents progress, but also the persistence of ignorance. The universe is full of objects, some of which cross our path, and our current detection network is better than it was, but nowhere near what it needs to be. The next big threat, the one that actually matters, might not be Apophis. It might be something we haven't found yet, something approaching from a blind spot, something dark enough, or fast enough, or unusual enough that it escapes notice until the last moment. And when that moment comes, the years we spent watching Apophis, the comfortable asteroid that gave us time to prepare and predict, might feel like a pleasant dream before reality insisted we wake up. Let's step back from the technical details, the orbital mechanics, the gravitational keyholes and tidal stresses, and ask a simpler question. What are 3i Atlas and Apophis actually teaching us? They're not just celestial objects with interesting trajectories. They're 2 sides of a cosmic lesson about proximity, danger, and the gap between what we think we understand and what the universe actually does. 3i Atlas came from interstellar space, a visitor from beyond our solar system, and it ignored us. It passed through our neighborhood without incident, without drama, without even coming particularly close to Earth's orbit. It was the perfect example of cosmic indifference. We exist. It exists. And those two facts have nothing to do with each other. Apophis is the opposite. It's a neighbor, an object caught in the same gravitational system as Earth, following an orbit that intersects with ours repeatedly over astronomical time. It's close enough that we've been tracking it for 2 decades. It's going to pass so near in 2029 that you'll be able to see it without a telescope. And unlike 3i Atlas, which will vanish into the void and never return, Apophis will keep coming back. Not every year, not even every decade, but on a schedule dictated by the mathematics of orbital resonance and gravitational perturbation. It's permanent. It's ours. And that permanence is what makes it dangerous. But here's the thing that doesn't get emphasized enough in discussions about planetary defense. The countdown to April 13th, 2029 isn't a countdown to impact. It's a countdown to data. On that day, we'll gather more information about asteroid flybys than we've collected in all of human history. Every telescope on the planet capable of observing near-Earth objects will be pointed at Apophis. Radar systems will map its shape to resolutions measured in meters. Spectrometers will analyze its composition with unprecedented precision. We'll watch how it spins, how its rotation changes, how Earth's gravity field reshapes it in real time. This is science at its most dynamic, a natural experiment we didn't have to design. We just have to observe. And what we learn won't just apply to Apophis. It will inform every model we build for every other asteroid in near-Earth space. The way Apophis responds to tidal stress, the way its orbit changes during the encounter, the accuracy of our predictions compared to what actually happens, all of that becomes calibration data for a detection and defense network that's still in its infancy. 2029 isn't a deadline. It's a data release moment. The information we gain will shape planetary defense strategy for decades to come. But there's a 7-year shadow lurking beyond that encounter. Even after Apophis passes in 2029, even after we've collected all that beautiful data and refined our models and congratulated ourselves on our predictive accuracy, the tracking doesn't stop. Because the asteroid will keep orbiting. It will swing out toward Mars, loop back toward Venus, return to Earth's orbital zone again and again. Each pass is another opportunity for gravitational interaction, another chance for tiny forces to accumulate into measurable changes, another test of whether our models can predict reality or just approximate it. The current consensus is that Apophis poses no threat in 2036, 2043, 2050, or any other specific date currently calculated. But consensus is built on data, and data from an asteroid that hasn't yet experienced its most significant gravitational encounter in millions of years is inherently limited. We're predicting the behavior of a system we've never fully observed. We're extrapolating from measurements that don't include the very event that might change everything. This is where humility becomes important. Not the false humility of saying we don't know anything, which would be inaccurate. We know a tremendous amount about Apophis. We know its size, its orbit, its composition, its rotation period. We can predict its position in 2029 to within a few kilometers, which is extraordinary precision for an object 340 meters across, moving at 7 kilometers per second. But we don't know how it will respond to forces we can model but not perfectly predict. We don't know if its internal structure will shift during the tidal stress event. We don't know if unknown volatiles will sublimate from solar heating combined with tidal flexing. We don't know what we don't know. And that's actually okay. That's how science works. You build models based on available data. You test those models against new observations, and you refine them when reality proves more complex than your equations anticipated. The problem is that in planetary defense, there's no room for iteration if the models fail catastrophically. You don't get to say, interesting result, let's try again, if an asteroid hits a major population center. The stakes demand accuracy on the first try, and the universe doesn't care about our demands. So the real countdown, the one that matters more than any specific date, is the countdown to comprehensive understanding. Understanding of not just Apophis, but the entire population of near-Earth objects. Understanding of not just where they are, but how they behave under conditions we've never observed. Understanding of not just the immediate threats, but the long-term patterns that govern how objects move through the solar system over centuries and millennia. We're making progress. 20 years ago, we couldn't have predicted Apophis's 2029 flyby with the precision we have now. 10 years ago, we wouldn't have had the computational power to run the multi-body simulations that map out possible futures for decades in advance. 5 years ago, we didn't have AI systems capable of processing sky survey data fast enough to detect new objects in near real time. The technology is improving, the science is advancing, the detection network is expanding, but the gap between where we are and where we need to be remains enormous. Consider what comprehensive planetary defense would actually require. We'd need to catalog every object larger than a few tens of meters in near-Earth space. That's millions of asteroids, most of which we haven't found yet. We'd need continuous monitoring of all cataloged objects to detect unexpected changes in their orbits. We'd need the capability to rapidly characterize newly discovered objects to assess threat levels. We'd need deflection technology that actually works, tested, and ready to deploy on short notice. We'd need international coordination frameworks that can make decisions quickly when time is limited. And we'd need public trust that institutions will provide accurate information even when that information is frightening. None of those pieces are fully in place. Some are progressing well, others barely exist. We're building the infrastructure to defend against asteroid impacts, while asteroids continue to cross our orbit on schedules that don't care about our readiness. It's a race between expanding our capabilities and encountering something our current capabilities can't handle. And races like that are won or lost, not by the fastest runner, but by whoever crosses the finish line first. 3I Atlas represented one kind of cosmic relationship, the stranger passing through, indifferent and untouchable. Apophis represents another, the familiar object that keeps returning, gravitationally entangled with our future. Both are real. Both exist simultaneously in a universe that contains multitudes. And the lesson they're teaching, if we're willing to learn it, is that danger doesn't come from malice or intent. It comes from proximity, from repetition, from the mathematics of orbits that intersect and gravity that interrogates. The universe isn't whispering possibilities. It's shouting them. It's showing us with every close approach, with every late detection, with every gravitational keyhole we calculate and worry about, that space is not empty and we are not safe by default. Safety is something we have to build, maintain, and continuously verify. It's a product of knowledge, technology, and vigilance. And all three of those require resources, attention, and the willingness to take threats seriously, even when they're not immediate. So, as Apophis continues its orbit, as 3I Atlas fades back into the interstellar darkness, as new objects get discovered and added to the catalog every week, ask yourself, are we listening? Are we building the systems we need fast enough to matter? Are we treating planetary defense as the existential priority it actually is, or as an interesting science project that gets funded when budgets allow? Because the countdown is running, not to impact, not to any specific catastrophe, but to the moment when our luck runs out and something appears that we can't track, can't predict, and can't stop. That moment might be centuries away, or it might be next month. We won't know until we've built the capability to know. And right now, today, in late 2024, we're still building. The universe has shown us what's possible. Now, it's our turn to show what we're capable of. The question is whether we'll be ready when the answer matters most.